Welcome everyone. I'm happy that you watched this video on that paper. The European Journal of Applied Mathematics asked me to give a short, like 10-minute introduction to my paper, Inhomogeneous Helmholtz equation in waveguides, existence and uniqueness with energy methods. I learned something like 5 years ago that solving the Helmholtz equation in unbounded domains is extremely difficult, or was not even resolved since 2016. So let's be careful. There's a lot of literature on unbounded domains in the sense of whole space or half space, but then with homogeneous media. And there's of course a lot on one-dimensional problems. But what I'm talking about is such a situation of a waveguide, so it's unbounded on one or in two directions. For me, it's now two directions. And the medium is periodic. And, well, astonishingly, the first result is by Fliss and Joly in 2016. That's a great paper in Archive of Rational Mechanics. They solved the problem. They use operator theory. I find that quite heavy machinery, and I was wondering since then, can you do also improve with energy methods? So very down to earth, you write down whatever, a Galerkin scheme or some proximate problem with the truncation or limiting absorption, and you take the limit and here's your solution, and not via integrations of paths in the complex plane. Okay, so and this paper is the result of these thoughts. So it is possible. I want to explain in which sense and what setting. So Helmholtz equation is this equation. You have some coefficient A, it's a positive, uniformly bounded above and below coefficient, only x dependent. I speak of a linear equation here. So it's a nice elliptic operator. We have the problem for some real number omega, something like minus Laplacian, u equals omega square u, so it looks like an eigenvalue problem, and indeed that's the point, that there are wave-like solutions. So, for example, sine omega x is a solution of that in the 1D a equal 1 case. So you have periodic solutions, yeah? So that's the idea. They don't decay at infinity, they remain of the same height at infinity. Well, solutions. In order to have a non-trivial solution, I put an F here, which explains the inhomogeneous Helmholtz equation. Waveguide is this geometry. It is specified here, so my domain in which I want to solve this equation is R times a cross-section. The cross-section is some bounded open domain. So in that picture it would be in 2 dimensions, and the interval would be S. R times S is the waveguide. A is this positive coefficient, and A should be one periodic in the x1 direction. If I move one to the right, I see the same A. Okay, and here's the theorem that is shown in this paper, namely, under the assumption that omega is a non-singular frequency. I will say something on that assumption, but I want to emphasize that in all the papers about existence and or uniqueness for such a geometry, there is such an assumption that omega is non-singular. A theorem says there's only one solution. And I'm specifying a little bit, what does it mean to be a solution? Well, it solves the Helmholtz equation that is written here in omega, in the weak sense. Of course, we need boundary conditions, top and bottom. Let's say Neumann boundary conditions that we can incorporate in the weak form of the equation without any difficulty. But the result is the same for Dirichlet boundary conditions. Yeah, so that's not an essential point. Here I introduce that in order to introduce also a norm that is very important for me in this proof. Namely, I don't only want, so I forgot to say that U should be locally H1, in order to say it's a weak solution. But I need some information on how the u behaves when I go to plus and minus infinity, and I wrote it in this form. I might have written u should be bounded, but actually when the coefficients are very rough, then I don't have the continuity of the solution. Maybe, huh? That's why I don't write it's bounded, but I say if I measure the L2 norm on any cube inside the domain, no matter where I put the cube, this is bounded. Yeah, so also at infinity, the u doesn't grow. Yeah, but I remind, we should not expect that the u decays. It will stay of the same height, plus minus infinity. And then we need some radiation condition. Okay? And well, what comes now is a word on what does it mean to be non-singular? How do I impose this radiation condition? And well, let's do that. So the omega non-singular means that I have a family of phi j plus minus. And that should be a finite number of waves. So each phi in this family is a solution of the homogeneous Helmholtz problem. Let me write for short a phi equals omega squared phi. It should be quasi-monotone, quasi-periodic. So phi of x plus E1 is some phase shift. I call the coefficient xi, that the real number xi, times phi of x for all x. Yeah, so when I go 1 to the right, I just make a phase shift of the function. And each of these functions has, so phi j plus or minus has positive for the plus sign or negative flux. What is meant by flux? Well, a simple calculation, namely testing this equation with phi bar and integrating over s and from some little r to capital R and taking the imaginary part, shows that the quantity d1 phi times a times phi bar integrated over the cross-section at the position r, the imaginary part of that is independent of r. Yeah, this is just by multiplication of the equation with phi bar, taking the imaginary part, then the bulk terms vanish because they are real, and what remains is only the boundary terms. So that is independent of r, and this is called the flux. So, and I want to have these basis functions with the positive and negative flux. Okay, and then the radiation condition, so let me make sure that this is clear now. Omega non-singular means now essentially there is a finite number of such basis functions that span the space of all solutions. Yeah, so here to guarantee that you have to work with Floquet-Bloch, that somehow you find all solutions by making quasi-periodic ansatz. And then the other condition is that every phi in this space of solutions carries energy either to the left or to the right. Okay, and then we pick such a basis. And then I can also write down the radiation condition. So in the classical form would be, so for given u, I mean a u that should satisfy that, there are coefficients alpha j such that u minus these coefficients j plus, this goes to 0 in an appropriate norm when you go with x1 to plus infinity. Which means, if you look at the far right, then u looks right. If you subtract the right-going waves, it goes to 0. So there are no left-going waves contained in u. So that would be a form to write down the radiation condition, or, which I find in the setting that I use a bit more convenient, I introduce a projection onto right-going waves, and I project u on some cube that we had before in this supremum. So I restrict u to r, r plus 1, this interval times s. So I look at u at the far right, I project to right-going waves, and that goes to 0 for r to infinity. Yeah, then I don't have to worry about norms, because this is then L2 convergence is the natural way of writing it. Yeah, here I'm not precise about the norms. So there are no right-going waves when you are on the very far right. So yeah, these are the ingredients of the proof. And let me say two more things. One is, do you only recover this known result here, or do you also find new results? And the answer is you find also new results. Let me just mention that in this paper, there's treated also a situation where you have, let's say, one periodic medium on the right, but another periodic medium on the left. Yeah, just to indicate, so it's truly different. Medium on the left and right, and in the middle you do anything, and you solve this problem, and you can say something about it. And let me warn you, the result is not there exists a unique solution, because there could be, even for f equals 0, there could be a solution of that problem, non-trivial solution. But the result is a Fredholm alternative. There's either a non-trivial solution of the homogeneous problem, or you can solve for every f this problem. So this is the second theorem in the paper. It's a Fredholm alternative for this problem. Okay, so this you can also do with the same methods. So let me say something about the method. It starts with an approximate problem. And the approximate problem is a truncated one. So we take the domain truncated from, I'm a bit rough now, from minus r to plus r, and solve there, and the solution is denoted by ur. Of course, the question is, what boundary conditions do you impose on these artificial boundaries? And here, in this paper, I reuse a construction that we introduced, Thomas Stonal and me, in another paper. Namely, we say, well, we construct such radiation boxes of width 1, and we say, let me indicate it with a picture, you should be something right going here, you should be something left going here, otherwise it's free. Yeah? So you can see this is a good approximation of the problem. This is how we imagine U to be far outside. We don't imagine it to be 0. Yeah? So a Dirichlet condition would be very bad. We imagine it to be outgoing in the box, otherwise free. So, and it's a solution of the Helmholtz equation inside, and you have to couple the two conditions somehow in a good way, but that's possible with a good Lex-Milgram formulation. Okay, and now you analyze UR. And somehow the first case is that this norm of u that is written here, the supremum norm, I denote it like that, if that is bounded, then you are essentially done, because then, well, then you can take a weak limit. The weak limit is u, and u will be a solution. Also, a second case is easy, namely if, let me say, this supremum over all r of u, well, okay, is taken in a bounded region. Yeah, so in this norm there is a supremum over all r and z, and we assume this is taken in a bounded region. Then we have two subcases. So if it's bounded, we are done anyway. So we don't have two subcases. It goes to infinity. Yeah? So let's make it simple. So without loss of generality, I can say that, let's say, for r equals 0 it happens. Yeah. So u on the cube 0, 1 times s, the L2 norm, goes to infinity. And elsewhere it's smaller. Yeah? Then you make a rescaling argument. Sorry, ur is missing here. Then you take ur divided by this norm of ur. Okay, this is a new function. This is now bounded. This will go to some function v as r goes to infinity. And v will be a solution of the homogeneous problem because you divide by a large number. So these are solutions of the inhomogeneous problem, but with f divided by a large number. So in the limit, this is a solution of the homogeneous problem. And if there is no solution of the homogeneous problem, except 0, then you are done. Well, but only if this limit is non-trivial. Yeah? In this case too, the limit is non-trivial because, well, in this inner region, the supremum is taken. So if you divide by the supremum in the inner region, something survives. Okay, so now I conclude with this picture of what could go wrong. Here's a 0, here's a capital R, we have a solution here everywhere. Yeah? I indicated here. Somehow this should be the norm of the solution. Some norm. Well, the question is, can that happen? So if the norm is very large in the central region, case 2, then we don't have a problem. We do this rescaling argument and we are done. If it's bounded everywhere, we are also done. But what if the norm gets large at a point, let's say r over 2, far out, but not in a bounded region? What do we do then? And here comes a very, I find it nice, almost geometric argument, how you resolve that. If u is, so ur is meant here, if ur is a large function, it has right-going and left-going parts. Well, at least one of them is large. By construction, the u in this box here, this was the approximate problem, where is it? Here, was right-going in this box. Okay, does that contradict our flux equality? I mean that the flux is independent of the position. Well, no, it doesn't. Yeah, it could have here the flux 1 to the right, nothing to the left, and it could have here the flux 5 to the right and flux 4 to the left, gives the net flux 1 to the right, and no problem. Yeah, and the norm would be somehow this fancy calculation would be 9. Yeah, 5 plus 4, but of course it counts differently, but you get the idea. So it's hard to exclude that. Well, it's not impossible. Let's look at a new function in which we somehow subtract this part. So we take this minus this one that I subtracted. It's a new function. Yeah, I consider the UR. I look at the right-going part in this box, and I subtract this function, which is some phi j functions, some linear combinations thereof. I subtract them and look at the result. The resulting function is again a solution of the homogeneous Helmholtz problem. The resulting function is by construction only left-going in this bit, and it is something right-going in that bit. Now we can make use of our flux equality. The flux equality says that the flux here and here is the same. Here it is positive, here it's negative, so it must be 0. Okay, so the conclusion is this part must be 0. And this combined part must be 0. So I can argue like that. Well, the left-going part must be 0. We saw that. And okay, and then it is essentially a constant right-going function everywhere, which was the case. Yeah, then it's not higher up here than here. Yeah, but the right-going part is the same here and here. So this picture can be excluded by flux equality. That's the main part of the proof, because yeah, then in all these cases you can say, okay, the limit of the UR functions is my function U solution of the original problem. And you see by the method that you can treat also such a geometry, because these arguments only play a role on the far right or on the far left. Okay, so much about this article. Thank you for watching the video.